Hello, my name's Mike, M0MSN, and I've got a question. ATUs, antenna matching units, call them what you will. How do they work? Now, when you transmit through an ATU, after you've matched, got the antenna working as it should, if the antenna matching unit's at this end, the transmitter end, and then you've got, 15, 20 meters of coax cable before you reach the base of the aerial, what happens to all the power that's reflected from the aerial back to the matcher? Does it bounce backwards and forwards? Does it go to earth? Does it get lost in heat? How does the ATU manage to match the antenna to the transmitter? Is it magic? Don't know. So shall we explore that? I suppose what I really need to do is start at the very beginning. Why do we need an ATU? Well, I'm going to show you a little bit of physics, if that's the easiest way of putting it. I've just cut a half-wave antenna. I don't know what band that is. I'd have to measure it and work it out, but that is a half-wave antenna on some band. Okay, now on this particular band, let's see if I can make it a bit flatter for you, bear with me. Okay, so there's a reason why I've taped it to the bench there. Just let me get a tape measure a moment. Blimey, 42 centimeters. So our piece of wire is 42 centimeters long, because I've just measured it. So 42 centimeters long as a half wave would be 84 centimeters long as the full wave. 84 centimeters. What is 84 centimeters? Right. 300 divided by 0.84 centimeters equals 357 megahertz. So this piece of wire is a half-wave dipole. If we cut it in the middle and put up one side of our coax to one side and the center cord to the other side, we'd have a half-wave dipole here for the 357 megahertz band, or the frequency. So if we were to cut it and put our coax in the middle, we would have an impedance somewhere around 73 ohms in the middle. If we were to connect our coax to the very ends, we would have an impedance of around 3,000 to 4,000 ohms. Okay, the reason why there's a variation there, because it depends on what the material is, the diameter of the core, and also any imperfections. So it's not 100% accurate, but we can say it's between 3,000 and 4,000, which is why a 49 to 1 balun or a 64 to 1 transformer balun works so well with end-feds, because we know the approximate impedance on the end of a piece of wire. In the center, it's around 73. If it's cut, if it's not cut, it's actually 0. Roughly 0 ohms. So why do we need an ATU or a antenna matching unit? I hear you all shout, if we can create dipoles that have an SWR of 0 or 1 at the frequency that we want to use. Well, it's simple, really. Okay, let's see that we want to use the antenna that we've just made for the 40 meter band at 7/100, and it's 1 to 1, and we think to ourselves, well, we'd actually like to use that at 700 on the nose. Okay, so let's go down to 7 megahertz. SWR is 2. Look, our impedance is going down because the antenna is becoming too short for the frequency. So where our impedance is now 28, let's go down a bit further. So we're now at 6.9 megahertz. Our impedance is 22. SWR is 3.2. Way too high for our little transistor radio amplifier to cope with. So our transceiver won't like that SWR at all. Valve sets may still cope with it, but our little transistorized transceivers won't enjoy that SWR at all. So we need to match it. So let's take it up, up, up. So we get 0 SWR, which is there. That's 7100 or thereabouts. We can take it down. 700. Now let's say we need to transmit at 7.2. So we'll take it up to 7.2. Now all of a sudden the antenna is too long for the frequency that we want to use. So at 7.28, our impedance is 116 ohms, SWR 2.3. Again, it's too much for the poor little transistors to cope with. So we need to match this without changing the length of our antenna physically. And we can do that by using an L or a T matching circuit. Shall we start with a very, very basic circuit, okay, of how an ATU works? Is the light in the way? I think it probably is. Okay, look. So we'll have our SO, awful picture, our SO 239, which on this side will have a little centerpiece and okay, and we'll connect that to a 10 or 20 turn coil, okay, and from our 20 turn coil we'll connect this end to another SO 239, and this will go to our aerial. This side will go to our transceiver. Now, here, and this is the earth, and the earth. So here, what we're going to do is insert a variable capacitor. And there is our L network. Call it an L network because it's the shape of an L. If we put another capacitor here, that would then be a pi network because it makes a pi symbol. Anyway, we won't go there. If we put another coil here, it's a T. Anyway, let's just redraw this nice and neatly. Okay, so here's our L network redrawn. And we need to understand the relationship, if you like, between this transforming circuit, the impedance transforming circuit, and how it works with our transmitter. Now, our transmitter requires a 50 ohm impedance for it to be at its optimal performance, and our antenna isn't. Unfortunately, in this particular instance, our antenna is 1k ohms. Don't ask me why. It's just a figure I pulled out of the sky. Makes the maths easier, if you wish. Okay. So we have to transform our 50 ohm to 1000 ohm, or 1000 ohm down to 50 ohms, whichever way you look at it. So we have a 1000 ohm antenna. This is because it's not the right length for the frequency that we're using. If it was cut to precisely the right length for the frequency we're using, that would be a 50 ohm antenna if it was balanced. Okay, or in fact it would be more like 73 ohms, but we'll call it 50 ohms. Now, we are unlucky enough to have the antenna is slightly too short or too long, and it's represented by this 1000 ohm feed. Okay, 1000 ohm impedance measurement on the antenna. So we now have to match that 1000 ohms to get it down to 50 ohms to make our transmitter happy. You use an inductor in series and a capacitor in shunt or parallel, and that will match our K to the 50 ohms. But how does it match it? Right, okay. So we need to use some maths now to work out exactly how many ohms or how the value of the various components to bring that matching down to 50. Okay, and I suppose we need to start really with something known as the quality or the Q. Okay, now to work out Q, we need to know the load or the 1K, and we do know that, so we can put Q equals, well, we need to do it in square root for starters, otherwise nothing works, and we need to find Q, which is always set as -1 off of the square. Now we've got 1000 ohms on the antenna, and we're trying to get it down to 50. Okay, so we have, well, I'm going to have to use my calculator for this. So let's see if it's switched on. It is. Excellent. So we need to find the square root of these two. So it's 1000 over 50. Let's go to the side. -1. Because that's the way it works. We now press equals. And we'll just make that a proper figure. 4.35. Okay, so Q equals 4.35. So now we need to find C. Okay, so XC equals, and make this simple. Okay, XC equals the load, which is 1000, divided by our Q factor, which would equal, let's put that in the calculator. Hope this isn't too boring. 4.35 equals proper figures. All right, there we go. So our J is minus J 229.8. So 230. It's close enough. Okay, J is complex impedance. So it's minus 229.8. Now that's the impedance of the capacitor here. It's not the value of what we need, it is the impedance. To work out inductance, it's XL which will be 1000 times 4.35. Okay, and that will give us our, no it won't, will it? It's not that at all. It's not 1000, because it's the other side. So to find L, the XL, which is the impedance of L, we need to 50 ohms times the 4.3, which is our Q factor again. So let's do it. 50 times 4.35 equals, take it into engineering, 217. So this is going to be J2175. Okay, Scooby-Doo. So these figures are now we need to change these into actual Henrys and Farads. You know, I never knew that trying to explain maths was going to be so boring or so difficult to try to put on paper. But my goodness, it's dry, isn't it? It is really dry. Anyway, I'll do my best. Well, we're almost there. There's a couple of extra equations that we're going to need to to know to get there. The thing is, has anyone noticed anything yet? You've got plus 218 and minus 230. So these two almost cancel each other out, which means that this 1K, which has now got an impedance of 230 when it's combined with the capacitor, has got almost the same impedance as the inductor. So these two will start cancelling each other out. With a little bit of tweaking, we could get the inductor up to around the 230, which means that you know, we could perhaps tap the first coil, which will bring the inductance up, so we can get more of an impedance across it, maybe 230, and that will then cancel each other out, which means we'll be left with the 50 ohms. That's the relationship. Do you see that? Anyway, we need to find out the value of the capacitor and the value of the inductor in microhenries and also in picofarads, so that we can place them in place. The other thing, of course, is that we don't always know the impedance of our antenna as the frequency changes. So the impedance changes on our antenna if it's a fixed length antenna. This is why, after all, why we've got a tuning circuit, so that we can adjust our tuning circuit to allow us to use multiple frequencies on the same antenna. Hence why we have a variable capacitor, so we can vary the capacitance, which obviously then changes the impedance of this side of the circuit. And because we've got a variable coil, i.e. we've got either tap points or we've got a roller inductor, we can change the impedance of the coil as well. So they start cancelling each other out, which is why we use this circuit, because it cancels out the impedance that we don't want. It matches. Do you see the relationship? Anyway, look, enough talking about this side of it. Let's get the values of the components for this particular circuit. If we're going to use, let's say, 14 megahertz as our frequency. So let's set the frequency. Let's find out the value of the components we require to match our 1K to our 50 ohm transceiver. And then what we'll do in the next video is we'll actually build the circuit and see it in operation. Anyway, let's find the component sizes first. Okay, to find out what L is, this is L. L equals plus J over 2 pi times the frequency, and that will give us our microhenries. Okay, and to find the capacitor's values, it is 1 over 2 pi frequency times minus J. Okay, right, the long and short of it all. 14 megahertz is our frequency that we've chosen. Okay, 1K is the impedance of our antenna. So as it comes into our L circuit, it reaches the capacitor and the coil. The capacitor's in shunt position, which is in parallel, and the coil is in series, which is going to our transmitter. Okay, we have to treat this as two circuits, all right? So we split it in half, and it's our capacitor and antenna circuit on this side, and then our L circuit on the other side. So we need to find a value for the capacitor. To find that value, the easiest and quickest way I found, there are many other ways of doing it, but this is one of the easiest way, is to find the Q factor for the circuit that we're playing with. And to find the Q factor, you divide the antenna's impedance with the transceiver's impedance. So we find the square of 1000 over 50 minus 1. That's the equation. Okay, and we come up with a figure of 4.35. Hurrah, we'll hear us all saying. So we have this Q factor, which is now, you might see, useful, because we now need to find the impedance of our capacitor, and to find the impedance of our capacitor, we use the impedance of the antenna, which is 1000, divided by the Q factor. Okay, and the answer to that, it would be a minus J. Now, J is one of these engineering symbols that we use. Could be I, could be whatever, but we've decided to use J because I is in use. So it's our impedance figure, our complicated impedance figure. And because it's a capacitor, it's minus J. If it was an inductor, it's plus J. But anyway, we're minus J, and it's 229.8. I've rounded that up to 230 for future calculations. So we'll call it that, 230 at the moment, okay? And to find the L, it is almost the same equation, only we use the transmitter's impedance, which is 50, or aiming point, if you like, times the Q. So we're going to go 50 times the 4.3, blah, 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 blah. And that gives us our coil's impedance, which is 217.5, but plus, okay, because it's our coil. So we now need to transfer these complex impedance into values that we can now find off the shelf for our coils and our capacitor. So let's start with L, which is our inductor, the coil, and we use the complex impedance over 2 pi times the frequency, and that gives us 2.4 microhenries. 2.4 microhenries. And then we need to know what the, so we can write that down, 2.4 microhenries. Up there. Now, the capacitor. The capacitor is a different calculation, but it's the same basis. Again, 1 over 2 pi times the frequency times our complex impedance gives us 49 picofarads. Okay, 49 picofarads. So our capacitor is 49 picofarads. Are we getting there? We are getting there. I think we're getting there. So we've got the value of the components that we need, and yeah, long video this, so I can congratulations if you're still awake, but if not, it's a great cure for insomnia, obviously you've probably found out. So we've got the value of our capacitors and the coil. So in the next video we'll put that to use, and we'll build an L matching circuit or an L network out of an inductor and a capacitor, both variable. Hopefully, probably the coil will be tapped rather than a physical roller inductor. But we'll do a tapped coil, and we'll use a capacitor which I'll build from a kit, and we'll put it into use with the antenna for 40 meters, and we'll actually see it in action. We'll also put a few test bits and pieces in place so you can see where the SWR is, where the power is going, where it's and so on. Anyway, I hope you've enjoyed the video. I'm sorry it's a long one, and I appreciate if you have fallen to sleep, then congratulations. Okay, cheers for now. Thanks very much for watching, and yeah, don't forget to subscribe and press the little thumbs up and the like button. That would be nice. That is the like up there. Anyway, thanks very much for watching. Cheers for now. Bye-bye.